Hey guys, Miss Gosling here. In this video, we are going to go over nuclear decay. By the end of the video, you will be able to define nuclear decay and solve nuclear decay problems. So with that, let's go ahead and get started. So let's go ahead and start by talking about what nuclear decay is and why it happens. Nuclear decay occurs when the nucleus of an unstable atom spontaneously changes its nuclear configuration. This occurs because it increases the nucleus's stability, but let's talk about what changing its nuclear configuration means. So when I say changes its nuclear configuration, what I really mean is typically, there's a few things that can happen. So first, I could have a neutron that turns into a proton. I could have a proton that turns into a neutron. Or I could just have an electron change its configuration and release a photon. So the second thing I want to talk about is increasing the nucleus's stability. So a concept we're going to learn about in the next topic is something called binding energy per nucleon, which you can see is graphed on the y-axis here. The only thing that's important for you to know right now is that increasing a nucleus's stability means that we're increasing the binding energy per nucleon. So what that means is each neutron and each proton is more closely bound to the center of the atom because it has a lot more energy holding the whole nucleus of the atom together. So when we talk about increasing stability, we mean for our lighter atoms, our lighter elements, increasing the number of nucleons in the nucleus, so adding more protons and neutrons. And for my heavy elements, what I mean is losing some of those protons and neutrons. Now, nuclear decay can happen in a variety of ways, but just before I get into some of the nitty-gritty of that, what I want to talk about is just how we express atomic mass and atomic number. So I'm going to start with the example that we had at the beginning, or the last video of carbon-14. So carbon-14 has a nuclear mass of 14. So by nuclear mass, what I mean is the total mass of one atom in atomic mass units, which is another way to measure mass based off of the number of protons and neutrons that make up an atom. This 14, more importantly for us, is also the nucleon number. Nucleon number is the number of protons and electrons. Number of protons and neutrons. In the atom. So what that is all of the heavy subatomic particles that make the atom up. This 6 down here is the atomic number. So this is where you'll find it on the periodic table. It's number 6. And this tells me the number of protons. Now what's nice is that, therefore, if I know this, I know that my nucleon number is 14. And I know that's equal to my number of protons, which is my atomic number, 6, plus the number of neutrons. And so from this, I can actually really easily figure out that the number of neutrons in this atom is going to be 8. Now, one last thing I want to mention before moving on. The number of protons, that atomic number, is often given the symbol Z in IB physics. And the nucleon number is often given the symbol A. So what I would have, so if I have an element and I'm kind of trying to get just a general element, I'm going to say that my element has its symbol, whatever it is. I'm going to use XX for the symbol. The nucleon number is A on the top left, and the atomic number Z is going to be on the bottom right. So that's kind of just my general way to express the isotope that I have. So now that we've talked about why nuclear decay happens, let's get into the how. So there are 4 types of nuclear decay. The first, alpha decay, occurs when a helium-4 nucleus is released from an unstable isotope. So over here, I have an example of alpha decay, where I have uranium-238 turning into a helium-4 nucleus and thorium-234. One thing I want you to notice here is that my nucleon number A stays constant. So I have a nucleon number of 238 on the left, and on the right-hand side, I have 4 plus 234, which is equal to 238. So yes, my uranium nucleus, when it turns into thorium, loses 4 nucleons, but they don't just disappear, they go into that helium-4 nucleus. Similarly, if you look at the bottom here, my total Z is also constant. And this will be true for all of our nuclear decay equations. The total Z on the left will equal the total Z on the right, and the total A on the left will equal the total A on the right. I've written this up on my screen here, and you should make sure this is in your notes. This is fundamental to solving nuclear decay equations. So that's alpha radiation. The next type of decay I have is beta decay. Now, sometimes beta decay is split up into beta and positron decay. Other times it gets kind of treated as one thing. So we call kind of traditional beta decay beta minus decay because we gain an electron. And positron decay we call beta plus decay because we gain a positron, which is the antiparticle of an electron. I promise we'll get into what that all means later. So whenever I undergo beta decay, whether that's positive or negative, I am going to release either an electron and an electron antineutrino pair, or a positron, this guy here, and an electron neutrino. Now, we are going to get a little bit later into why the electron has an antineutrino and the positron has a neutrino. But the reason that both of these two particles exist is because my momentum in my equation needs to be conserved. For my neutrinos, I'm using the symbol nu, which is the Greek letter. And for my antineutrino, I just add a bar over the top to show that it's an anti-particle, not a real particle. And again, we'll get into a little later what that actually means. Just like with my alpha decay here, you can see that my total nucleon number is constant. So I go from a nucleon number of 131 to a nucleon number of 131 on the right. And my product has a total atomic number Z of 53, as is the case as well on my right. 54 minus 1 gives me 53. So in all these cases, I'm balancing equations just like you were in chemistry. You can see the same thing is the case here with my positron, and just don't forget, again, those neutrinos and antineutrinos. The last kind of decay is gamma decay. Gamma decay has no real released physical particle, but what does get released is a photon. This is a very ugly photon that I've drawn here. Let me try again. We use the symbol gamma for a photon. And what that represents is a release of energy when the electron configuration changes to something the nuclear configuration changes to something that's just a bit lower energy and more stable. So we have here nickel turning into nickel plus gamma radiation, with this star here meaning nickel in an excited state versus nickel in its kind of comfortable base state. So let's go ahead and look at some examples. So thorium-234, so that's going to be TH234. And just to note, this here is always my A, my nucleon number. Is going to undergo negative beta decay. What nuclide will be generated as a result? So negative beta decay means I'm going to release an electron and its antineutrino and some mystery element that I don't yet know. So the first thing I'm going to mention here is your IB exam, you are not going to have to use a periodic table for this. I find for myself it's pretty good practice to just get used to using a periodic table for these questions, so I am going to be doing that. So if I look at thorium on my periodic table, I can see that its atomic number is 90, which means that whatever is getting released, Z, so if I'm going to call this again XX with its own A and Z. So I know that 0 plus A has to equal 234. So that means that the nucleon number for my new atom has to be the same as my old one. since my electron is not a nucleon, so it's not going to change the nucleon number. And then Z. I know Z minus 1 equals 90, which means that Z has to be 91, which according to my periodic table, which I have in front of me, is palladium. So I'm going to write a 91 here, and then instead of XX, my kind of stand-in letters, I'm going to write what actually is generated. And here you go. There is my decay sequence. Let's do another example. So we're going to take that same thorium-234 isotope, so that's 234 and not 2,340, and 90, as it's because thorium always has a nuclear number of 90. And that's going to undergo alpha decay this time. So that means the helium-4 nucleus is going to get released. So if I look at the value of A for my new atom, I know that 4 plus my new value of A has to equal 234. So that means that there's only 230 nucleons left over for my new isotope. That also means that it has to have a nuclear number of 88, since 88 plus 2 equals 90, and my value for Z has to balance on both sides. So I'm looking at my periodic table, and I can see that the element with atomic number 88 is Ra, radium. So here is going to be the daughter nucleus, radium-230. One more example. Strontium-90 decays into an isotope of yttrium. Write down the nuclear equation for the decay. So I'm going to start with strontium-90. And I'm going to search my periodic table for strontium, which has a symbol of Sr. So looking at my periodic table, strontium has an atomic number of 38, and yttrium has an atomic number of 39. So what that means is I need something with a charge of -1 to balance things out. When I look at my types of decay, what that means is I must be undergoing beta minus decay, which means yttrium is going to have the same nuclear mass, the same nucleon number as strontium, but it's going to have a different nuclear number. And I, of course, need my electron antineutrino to balance out the momentum of my electron. And again, we will get into why it's an antineutrino a little bit later in this unit. So here is my nuclear decay equation for strontium into yttrium. So instead of knowing what kind of decay I underwent, I was able to figure out what has to happen to Z, and therefore what kind of decay can this possibly be. One hint here is there are really only those 4 options for decay. So you're not trying to figure out of a million different pathways how could strontium get to yttrium. Instead, we're saying, okay, I know that strontium is undergoing either alpha, beta, or gamma decay, so which one is feasible here? And since my value of Z is changing, I know that it's going to be beta decay. So I want to look at one other way that nuclei can change, and that is through electron capture. So when iron-55 captures an electron, so let's start with iron, which is a symbol of Fe, and an atomic number of 26, and it's capturing an electron. So what that means is that electron is one of my products, not one of my reactants. So now we need to see what's going to happen on the other side. So I have manganese, and manganese has an atomic number of 25, and it can have a mass of 55. And so what that means is instead of having this beta decay happening, what I have is an electron being added to iron, and then to balance out its stability to turn it into a stable atom instead of a charged ion, one of my protons here, I have one fewer proton in manganese, and so what it's done is it's turned into a neutron. So again, electron capture is another way that a nucleus can decay. And the difference between nuclear capture and beta decay is when we talk about capturing an electron, that electron is a product, not a reactant. So with that, I think it's time for takeaways. So first of all, unstable nuclei undergo radioactive decay. And there are 4 kinds of radioactive decay: alpha, beta plus, beta minus, and gamma. So with that, I have a lot of fun decay equations for you to solve. So best of luck and happy solving.